My name is Daniel Kerwin. I'm the Business Development Manager at ProLon. And today we are going to look at the different kinds of zoning systems which we are able to control using ProLon's controllers. So at first I have a little PowerPoint presentation which will go over the basic features of each kind of system. What are the different kinds of components which we will use. And then once I'm done on the PowerPoint side, I'm going to jump onto the software so we can see these systems, how they would look on the computer and how we can set it up using the software. So first of all, there are two kinds of zoning systems. So whenever people have a project and they're talking about a VAV zoning projects, there are two basic principles. One is called the changeover bypass system, or also known as VVT. So the main features of this kind of system is on the temperature control side is the zones. Each zone is going to create either a heating or cooling demand, and then through a voting system, it is going to determine whether the unit is going to enter heating or cooling mode. And as a generality, we will also find that the zones tend to not have any kind of peripheral heating, whether it's duct heaters or baseboards or zone valves. Because the general idea is that the unit or the rooftop unit or the air handler is able to heat or cool the space based on the demands of the zones. One of the other features of this kind of system is the static pressure. So how are we going to control it? Well, in this kind of system, we tend to control the static pressure in the ducts with a bypass damper. And at the zone level, we tend to use pressure-dependent actuators or pressure-dependent zone controllers. So in this case, we are controlling the airflow to the space based on damper position. So these are the main features for a VVT system. And then we get into the true VAV. So it's a little bit different. On the temperature control strategy side, well, instead of the unit responding to either heating or cooling calls coming from the zones, the unit tends to provide cool air all day long, whether it's a fixed 55-degree set point or if there's some kind of reset. And then at the zone level, every zone would have some kind of peripheral heat for that space. So whether it's a reheat coil or a zone valve or something like that. And so the general idea is that the unit is providing cool air all day long. So if any zone needs any cool air, it is already there available. And then if the space needs any heat, well, then it'll just activate its own peripheral heat at that point. In terms of the static pressure, we don't use a bypass generally. In this kind of system, we'll use a variable frequency drive instead. So instead of just recirculating the air, we will literally slow down at the speed of the fan to meet the static pressure needs for the system. Also at the zone level, it is not pressure dependent, but they are pressure independent controllers. So that means instead of controlling the airflow to the space based on damper position, we control the airflow based on the airflow readings. So we are actually measuring what the CFMs are to the space, and we are modulating the damper to achieve specific airflow values, if you will. So these are the two general ideas of different zoning systems. With ProLon, we are able to cater to both kinds of systems. And just so you know, we have seen some a little bit of mix and match sometimes, where some people will take one concept from one system and they will apply it to the other one. For example, in a VVT setting, generally the zones do not have any kind of reheat, because the unit is supposed to supply hot and cold air to the spaces. However, I have seen in my experience some VVT systems where some of the zones might have some peripheral heat. So just because these are the general guidelines, it doesn't mean that every system is set up exactly like this. Now, on the ProLon side, when we're looking for the zoning rooftop controllers, well, ProLon has two different platforms. There's the C1000 and then there's the M2000. And within each platform, we have two different profiles. There's the C1000 RTU, which is for zoning systems, and the C1000 RTUS, which is for single zone units. So in that case, we do not use the RTUS for a zoning system. We must go with the RTU. And the same can be said for the M2000 platform. So we have the PLM 2000 RTU, which is dedicated for zoning systems. And there's the M2000 RTUS, which is for single zone systems. Now, in this presentation, we are going to focus on the RTU profiles, and we are not going to look at the RTUS because that's for single zone applications, which is not what we are talking about today. The main differences between the C1000 and the M2000 platform really comes down to the amount of inputs and outputs. So the C1000 has 4 inputs and 5 outputs, and it is not able to handle a schedule on its own. So it needs another device, typically a network controller, which will give it its own schedule. And then on the M2000, it's got more inputs and more outputs. It's got 9 inputs and 8 outputs. It's got a built-in time clock with scheduling and annual holiday calendar as well. So if you just kind of compare these two, just think that the C1000 is the light version of the controller and the M2000 is the full version of the controller. Now, in terms of zoning systems, I'd say 9 times out of 10, we will go with the M2000 because it is able to achieve more. So what are some of these sequences which each one is able to control? Well, with the C1000, it can basically act like a basic thermostat. So we can control the fan, we can control the heating, whether it's multiple stages or if it's modulated. We can control the cooling if it's staged or if it's modulated. And the thing with the C1000 is that it is unable to control any kind of static pressure. So this is for constant volume systems, this one, or unless there was already something in place to control the static pressure. And the C1000 can also be used in an application where, in case you want to use averaging, so let's say we have multiple spaces with multiple temperatures, and we kind of want to average all that and report that back to a unit. Well, then we'll typically use our thermostat, one in every space, the PL-T1100. And then all those thermostats report back to the C1000 rooftop, which will then make the average of all the demands, and then it'll decide whether to enter heating or cooling. On the M2000, well, we have the same on the fan, heating, and cooling aspects, but with the additional inputs and outputs, we're able to control a lot more. So within this device, we can control the static pressure, whether there's a variable frequency drive or a bypass damper. We can control the outside air damper, so for the economizer sequence for free cooling. We can even connect a CO2 sensor into this controller. So now we're monitoring the CO2 levels, and we can play with the amount of fresh air which is being introduced into the system. With this device, we're also able to connect a humidity transmitter directly into it for dehumidification purposes. And we can control some exhaust fans as well. If ever there's a general exhaust fan based on occupancy, or if there's a power exhaust within the unit, which we want to turn on and off based on the economizer damper position, we are able to do it with this controller. So in terms of the wiring diagram, I'm not going to spend too much time on the wiring diagram, but just so you see, here's the C1000. So we can see the 5 outputs at the bottom, and then just above it is where we connect the temperature sensors, such as for the supply, return, outside. And then when we look onto the M2000, well, once again, we just get more. So on the right-hand side, we have all the inputs preset. So once you get this controller, all the inputs and outputs have already been preset for these specific settings. So the contractor who's going to install it, they do not have to specify in the software which input is going to read the outside temperature, which input is going to read the supply, which output is going to do the fan or the cooling stages. So just like with most ProLon controllers, everything is predefined. So that way the contractor who installs it, he can just arrive with his sensors and he can connect them directly into the controller. And then he can access it with the software, and then he can change different settings from there. So it is a plug and play system. On the zone controller side, so we have 2 different controllers here on screen. There's the VC2000, which is for pressure dependent systems. So as you can see on the picture on the top right, there are no ports to connect pitot tubes to the airflow sensor in the VAV terminal. So these VAV controllers are designed for VVT systems. And then there's the VC2000PI, which is the pressure independent model. So it is virtually identical to the one above it. However, you'll see on the bottom in the middle, we do have the high and low ports to be able to connect the airflow sensor so that we can measure what's the amount of CFMs passing through the VAV terminal. We also have another VAV controller, which is the C1000, and it basically mimics the VC2000, which we saw before, but the main thing is that it doesn't have an actuator already on it. So this is if we want to reuse existing actuators, it can control either a floating actuator or a modulating one. And just like the VC2000, well, it comes in 2 different models. It comes in the pressure dependent model, so that's without the airflow sensor. And then we have the pressure independent model with the airflow sensor. And then lastly, in terms of zone controllers, it's important to bring this one up because the T1100 thermostat, it can act as a zone as well. Now, the idea behind this is that sometimes in some systems, maybe we've got a dozen zones with dampers. So we'll use either the VC2000 or the C1000. And maybe there's another space which doesn't have a damper. However, we still want it to be included in the heating and cooling load calculations, which is driving the unit. And perhaps in that space, we also have some kind of peripheral heat, like maybe there's a zone valve, or maybe there's a duct heater, and there's no damper into the space, so there's just constant volume air coming into the space. Well, sometimes we'll find some reheat coils right there to be able to ensure that if the space gets a little cool, well, then we can reheat the air coming into the space. Also, just touching on what I mentioned before, when I was talking about the C1000 RTU, which could deal with averaging, well, we'd be using as many thermostats as we want, and then we would basically average all of the demands together, and then that would be sent to the C1000 rooftop, which would then decide whether to heat or cool. In terms of the network communication, well, it's a basic daisy chain, as we can see there. So we can have up to 127 controllers on a single system. So this is not just about one rooftop with 126 zones. No, you can mix and match as much as you want. So there's no limitation of how many zones can go beneath one rooftop. And it doesn't matter whether it's a C1000 or an M2000, that has no consequence on this at all. So we do want to use shielded wire, and that is one of the most important things. We typically advise people to use 24 gauge, a twisted, shielded, low capacitance cable. I've seen other people use a 22 gauge and it works just fine. If ever you're reusing existing wire, I've seen a lot of people do that and it works just well. I'd say just one of the main things to look out for is the shielding. So just make sure that the wire which we are using does have a shield. So it's not just about having one rooftop with a lot of different zones. We can have multiple rooftops or multiple master controllers, whether it's a rooftop or a heat pump or a makeup air or something like that. And once again, you can mix and match as much as you want, as long as we are within 127 controllers on a single network. And if ever you have more than 127, let's say you have a project where you have 200 controllers, well, at that point, we could maybe just separate it into two separate networks. So let's say it's a two-story building and there's about 100 controllers on each floor. Well, here's an example where we could say, well, we'll do the first floor will be one system and the second floor will be a second system. So in terms of the networking aspect of things, just a few important points here. So we have number one, it must be a daisy chain, as we can see here on the top. And each controller needs to have an address. So in this case, I address all my controllers sequentially from address 1 all the way to address 5. And as we can see here, that would be a good choice. Now, in the bottom example, let's say we have different zone controllers. They all have sequential addresses as well. However, they are not in a daisy chain. It is more of a star kind of configuration. Well, that is a no for ProLon. So it must be a daisy chain. Number 2, we can have a rooftop in the middle of the chain. So the rooftop does not have to be at the end. It can be in the middle, no problem. We just might have to change a jumper, which is already on the controller. So if ever you have a building where maybe we have an air handler or a rooftop and it's centered in the middle of the building and you've got some zones going to one side and you've got another set of zones going to another side, you don't have to do the daisy chain where the rooftop is at one end. But generally, we want the daisy chain to take the shortest path possible. So in that case, it would be advantageous to be able to network the rooftop controller in the middle so that we don't have to loop over it again in case it is at one end. And something else which this one shows you is that the addresses are not sequential. We can see that the rooftop is number 3 and the other 4 zones are kind of randomly numbered at 12, 21, 46, and 52. Well, this is okay. The addresses do not have to be sequential. As long as the daisy chain is respected, that is what is most important. And maybe just to help people out, we do think that it is easier when you do address the controllers in sequence. So, for example, I typically advise people give the rooftop an address such as 10, 20, 30, 40, and then the zones of, let's say, rooftop number 10, well, then the zones would be 11, 12, 13, 14, and the zones for rooftop number 20 would be 21, 22, 23. And so that way we're able to pair together, if you will, which zones should be with which rooftop controller. And then in the case where we do have a daisy chain, But in this case, during installation, perhaps the addressing wasn't done quite correctly. So in this case, we have duplicates. So we've got 2 controllers, which are number 1, 2 controllers, which are number 3, and 1 controller number 2. Well, this is not going to work either, because then when the software tries to talk to controller number 1, both of the devices are going to respond at the same time, and we are not going to be able to configure them properly. Okay, so in terms of a VVT setting or the changeover bypass system, how does it work? So number 1, it starts at the zone level. So each zone, whether it's the VC2000 or the C1000 or the T1100, each zone creates a heating or a cooling demand based on the actual space temperature and the zone set points. So as the space temperature starts drifting above or below its heating or cooling set points, then it starts creating a demand, whether it's a heating demand or a cooling demand. And also each zone has a voting weight as well. So we are able to change these voting weights. We can choose either to have each zone to have an equal voting weight as everybody else. We could increase voting weights of specific zones, so that way they have more influence on the system than the other ones. And likewise, we are even able to remove their voting weight entirely. So the zone is still on the system. However, it does not have any influence on the rooftop, whether it's going to enter heating or cooling mode. And in terms of the damper control, well, the VC2000 or the C1000 VAV controllers, they always try to satisfy the zone demand of their specific space. And how do they do that? All they're doing is they're looking at the supply temperature of the air coming from the unit. So the damper will only open if the supply temperature is favorable to the zone demand, or what is the zone asking for. And the zone damper is going to close either all the way or at least to its minimum position if the supply temperature is unfavorable to the zone demand. And so how does it know whether the zone temp is favorable or unfavorable? Well, all it does is it basically compares the temperature coming from the unit to its space temperature. So if the air coming from the unit is colder than the temperature in the space, then it is going to deem that it is cold air coming from the unit. And if the temperature of the air coming from the unit is warmer than what the space temperature is, well, then it's going to deem that there's hot air available to it in case it wants to open up its damper on a heating call. Now, at the rooftop level, so number 1, he is going to receive all the heating and cooling demands from every zone. So what does it do with all of these calls? It's getting all these different heating, cooling demands with different voting weights. So what does it do with it? Well, the rooftop controller, it will filter all these zone demands through something that we call math functions. And in the next slide, I'm going to show what different math functions we have. And the basic idea is that with these math functions, we are going to assign each math function to drive the heating and cooling outputs of the controller. Now, within this device, we're also able to set different priorities, whether the priorities are set manually or we can change them automatically based on the season, so that the rooftop will either respond to heating calls or cooling calls first. So we are able to configure that within our system. So on the math function side, so we have 5 different strategies. Number 1 is the weighted average. So with this, it takes the average of all zone demands. So it literally puts together all heating and all cooling demands. And then it's going to combine them all together, and it's going to come out with an average. A lot of people tend to use this specific strategy right out of the gate, but there's a reason why we try not to do it when we have many zones. And the idea is that a heating demand is positive and a cooling demand is negative. So when you combine positive and negative cooling zone demands all together, well, then they tend to cross each other out. So if ever you had a system of 10 zones and 5 zones were asking for full heat and 5 zones were asking for full cooling, the weighted average would be 0, and then the unit is not going to heat or cool. So that's why we tend to not use the first one when we're looking at a VVT system. The next one is what we call weighted average cooling only. So in this case, this function only looks at all the zones calling for cooling, and then it makes an average. So it's basically the cooling load of all your zones. The third function is weighted average heating only. So this does the exact same one as the previous, except for it does it for all heating demand. So it looks at all the zones with the heating demand and only those, and it makes a weighted average out of that. So number 2 and 3 could essentially be directly associated with the heating load and the cooling load of all of the zones. And then we have maximum cooling. In this case, it doesn't even look at the voting weights of any zone. It doesn't care about it. It's what is the highest call of cooling coming from any zone. Or the last one, maximum heating. What is the highest heating call coming from any zone? So which strategy do we want to use based on what kind of size system? Well, we tend to advise use the weighted average cooling only and weighted average heating only if you have 4 zones or more. And if you have 3 zones or less, we tend to advise go with the maximum heating and maximum cooling for that. Now, just keep in mind that these are general guidelines. Every system is unique, and we always have to take that into consideration rather than just blindly putting settings in. Sometimes we have to see how the system reacts, and then maybe we can adjust our strategy. So that's how we'll do it with a VVT system. And then on a VAV system, so for a true VAV system, it works a little bit differently because number one, it is not a voting system. So the VVT is like a voting system where each zone will vote for heating or cooling, and then the rooftop decides what to do. With the true VAV, it works differently. All the zones are basically expecting that the unit is going to be supplying cold air all day long. So the damper tends to only open on a cooling demand. And since these zones tend to have some kind of peripheral heat, whether it's a reheat coil, a zone valve, or perhaps it's a fan-powered VAV box, well, then it's going to activate its peripheral equipment on a heating demand. Now, just so you know, I know that some of these systems also have a morning warm-up sequence as well. So in that case, the zone damper will open up in the morning only if the zone is asking for heat. But if the space is satisfied or asking for cooling while the unit is in warm-up mode, then the damper will stay closed or at its minimum. So on the rooftop controller, its main function is to supply cool air all day long, whether it's a fixed set point or whether we want to reset that set point based on something else. And since the zones are actively not voting for heating or cooling, well, we do have to ensure some kind of warm-up function. So every morning, it's going to enter a morning warm-up sequence based on a few factors, such as outside air temperature, and the return air temperature as well. And so the idea is that the rooftop is going to go into heating mode until we're able to bring up the return temperature of the unit. And as we can see at the bottom, no math functions are needed for a true VAV system, so we don't have to worry about the 5 functions which we looked at before. Okay. And now just to conclude the PowerPoint, here's just some additional features which we offer with the Rooftop controller. And this is both for the C1000 and the M2000 Rooftop platforms. So one is a morning warm-up to disable zone outputs. So with this, the idea is that when the system becomes occupied in the morning, whether it's a VVT or a VAV setup, let's say it was a cold winter night and all the zones went into nighttime setback. And so when the system becomes occupied in the morning, well, it's quite probable that all the zone temperatures have gone down because our set points have gone down as well. So maybe in all the zones, it'll be about 65 or something like that. So then when the system becomes occupied first thing in the morning, whether it's VAV or VVT, what would probably happen is the rooftop will start heating and all the peripheral heat might turn on as well, whether it's reheat coils, duct heaters, fan-powered boxes, and so on. So we'll see this a fairly large energy spike in the morning because all the zones start heating and the rooftop starts heating all at the same time. So with this function, we're able to disable all the peripheral heat of the zones for a configurable delay. So for example, maybe we might set that delay for 1 hour. So in the morning when the unit becomes occupied, no reheat coils or duct heaters or zone valves or fan-powered boxes can turn on. Only the rooftop or only the air handler can warm up the spaces. And then after that delay, whether we choose half an hour or 1 hour, once that delay expires, then all the peripheral heating devices will be permitted to turn on. So this is considerable energy savings every morning right there. We have another feature called priority cooling zones, which I'll say applies a bit more to VVT settings, which is particularly useful for conference rooms or high cooling load spaces. So the general idea is that if ever we deem one zone as being a cooling priority zone, for example, a conference room, if ever that space starts asking for cooling, well, then its own individual cooling demand is going to drive the cooling of the rooftop unit. Even if all other zones are satisfied or something like that, this zone is going to take over simply because we've deemed it what we call a priority cooling zone. So we've seen this in conference rooms because when we're talking about a VVT system, every zone has a different voting weight. Well, it's a little bit tricky with a conference room because a conference room, number one, it is empty probably about 90% of the time. When it does fill up, it tends to fill up quite quickly with a lot of people. So there's going to be a cooling request very quickly coming from that space. And what people would usually do is they just give it a higher voting weight than all the other zones, which that will do the trick. However, the downside is that when that space is empty, which is 90% of the time, well, now you have this zone with the heavy voting weight, which is empty most of the time. So we're not exactly helping ourselves here. So by using the cooling priority zones, we are able to cater to their cooling needs a lot quicker. Another feature we have is we have the ability to disable zone outputs. So on the VC2000, on the C1000, and on the T1100, we can disable the outputs based on outside air temperature. So maybe we have a project where once in a while the reheat coils will activate because there's a heating demand from the space. However, it's 100 degrees outside. So we've seen this where some building owners wanted to limit what the basically what the heating output capabilities were, especially in summertime. So people would get heating bills during the summer, even though it was a very, very hot summer. So what we're able to do is we could disable it based on outside air temperature. And we can pick and choose which controller this applies to. So it's not a blanket measure, which will be enforced to all the zone controllers. We can pick and choose, okay, only this controller it will be applied to, and on this other one. We're also able to enforce certain peripheral heating. So let's say we have a large showroom which has a lot of windows, and maybe we have like a modulating three-way valve for some baseboard heat. Well, instead of waiting for the space to get cold, because we know it will get cold since there's a lot of windows, instead of waiting for the space to get cold, and then that cold reaches the thermostat, which will then command the valve to open, what we could say is set a rule, something like, if ever it gets to -5 outside, well, I want those three-way valves open at least 10% or 20%. So even if the space is comfortable and maybe it's not asking for heat, we're still going to let the hot water valves modulate a little bit to give off a little bit of heat, and then it's going to create like a heat shield, and then we're going to slow down the cold from creeping in. And then lastly, we have a tool, which is just a zone damper override command. If ever we want to force all zone dampers open or closed, we are able to do it from the software without going up to each wall sensor or up to the VAV controller and playing with set points. We have a central command. So that's about it on the PowerPoint side. Sophie, do we have any questions?
I don't have any so far.
Okay. So what I'm going to do is I'm going to open my focus here. So I'm going to just continue as a guest here. I'm going to create a new project. And I do have my demo board right beside me. I've got one rooftop with 2 zone controllers. So I'm going to connect with my adapter. So I know that I have a zoning rooftop. So as you can see on the left-hand side, we do have zoning rooftop, zoning heat pump. So I know I have a rooftop. I'll just drag and drop it in. And I know what the address is. So I know that it's number 20. Okay, and it pops up. I also have 2 zone controllers, so 2 VC2000s. So I could go here to zone and drag it in and put the address. But we have a tool which can help you make the controllers pop up quicker. So if you just right click on the rooftop, we have an option here that says get list. So when you click on this, it puts a call on its subnet, and all the controllers on its subnet are going to answer back. And there we go. So I got my 2 zone controllers, which have popped up. So at the zone level, we can see the space temperature, the set points, the individual demand. And on the left-hand side, zone number 1, we can see its damper position. So it's 10% open. And the other one has flow. So we know this one is pressure independent, and this one is pressure dependent. So if I just take a quick look at these, I'll just double click. And so here's the default view for the pressure dependent VAV controller. And if I double click on this guy right here, now I got the pressure independent view. And the main difference between these two is I can see the airflow sensor right here. Okay. Now, if I jump up onto the rooftop, I'll double click. So here's the default view for a rooftop controller. So once you receive a zoning rooftop, this is exactly what it is going to look like. So we've got our cooling coils, our fan, our heat, temperature in the supply, return outside. Here's the economizer damper with the damper position. We can see the time clock right here. And I can see the bypass damper as well as static pressure. So let's say I want to go look at a few of these things. I could, let's say, I want to go look at the cooling. So here we can choose how many cooling stages do we have. So we can go up to 4 stages. So this is for larger units, but typically ProLon fits really well with 25-ton units and smaller. And as you'll see here, we have the demand source, and now it's referring directly to our math functions, which we had been talking about. So when the control mode is demand in cooling, we know that it is set for a VVT style configuration. So here I can see my set points, the differentials, minimum on time, minimum off time, and interstage activation and deactivation delays. So with these values, we can make sure that the unit will not be a short cycle. Now, if I go look at the heating side, config heating, well, here's a little bit different, but we have digital output 4 for heating, digital output 5, and analog output 1. So here's where you determine which output will be your first heating stage, your second heating stage, or if we want to do modulated heat, then we'll just use the analog output. And you'll see at the top here that he also has a heating demand source. So let's go take a look at those math values. So I can just do network math right here. And so when you get the controller, by default, it is going to look like this. All 5 functions are at weighted average. But so here's where we want to change it. So we have weighted average, maximum heat, maximum cooling, weighted average heating only, weighted average cooling only. And then we have other functions here, but I'm not going to get into it because it doesn't pertain to zoning particularly. So like I said, in the case where we had 4 zones or more, I'll choose math 1 to be weighted average cooling only, and math 2 will be weighted average heating only. So I know that math 1 is only looking at zones for cooling, and math 2 is only looking at zones for heating. So math 2 will drive my heat, and math 1 will drive my cooling. So I can just go make sure. I can just double click right here. So it says demand source is math 1, so that's good. That's my weighted average of cooling. And if I go into the heating, well, I don't want my cooling math to drive my heat. No, I want my heating math, which is math 2. And there we go. So that is how we would set it up on the math functions. Math 1 drives cooling and math 2 drives heat. Now we can also see on the bottom left on the main page, we can actually see what those math values are. And I can change it by doing config edit display. And I could show math 2. And I could actually rename this. I could call this my cooling load and call this my heating load right there. And so now when I come back, here we go. So I can see the cooling load is at 0, which is normal because no zone is asking for cooling. And my heating load is 50%. Well, I've got one zone asking for 100% and the other zone is asking for nothing. So it makes sense that the heating load would be 50%. Okay. Now, in terms of the priority, let's say I change this up a little bit. I'm going to force this zone to go into full cooling mode. So I'm just going to do config temperature, and I'm going to bring his set point down to, let's say, 65. So now I have this zone, which is now asking for 100% cooling. And if I go back onto the software of the rooftop, well, now I can see that my cooling load now is going up. So now we have a case of I got a 50% cooling load and I have a 50% heating load. So this is obviously based on those math functions. If I went to change it up and I wanted to follow my own advice, which I said, if there's 3 zones or less, I said I prefer to use max heating and max cooling. So following that logic, I'll choose max cooling and max heating here. And then we're going to see this. So we're going to see both of these are going to jump up to 100%. because we're no longer looking at the weighted average. We're just looking at what's the highest call period. So now the zone wants full heating and it wants full cooling. Who's going to win? What is the unit going to do first? Well, for that, we do config priority. So when you get it out of the box, we have manually set it to priority cooling. So in that case, when in a case like this, the cooling side is going to prevail. So the unit will enter cooling mode. And once we've satisfied the space enough to turn off the cooling outputs, only then will the unit switch into heating mode. And the reason why we defaulted it to prioritize cooling manually, it's simply because oftentimes zones might have another source of heat, whether there's a baseboard or a zone valve or some kind of or some other peripheral heating source. However, we are able to change it based on the outside temperature. So like I said, we can change the priority based on the season, and we do that based on the outside temp. So if the outside temperature is above this value, so if it's above 46, then we prioritize cooling first. And when the temperature gets above, when it gets below 46, then it's going to prioritize heating. So just know that this value is configurable, so you can play with this changeover set. Okay, so those are the basics for a VVT system. If I were to jump onto a VAV system, so to change it from a VVT to a VAV, I have to go onto the cooling menu, and instead of being demand, I'm going to change it to a supply temp. So the control mode is a supply temperature. So it says calculate the supply using, so we can use a fixed set point. So I could say I want to maintain 55 Fahrenheit all day long. We can reset it based on the outside temperature. We can reset it also based on the return temperature. And with ProLon, we added our own flavor to it, where now you could reset it based on a math function, and you get to decide what that math function is. Is it a weighted average of cooling of all the zones? Is it just the highest call of cooling coming from any of the zones? So you get the idea. So we have different strategies to determine what the supply set point will be for this unit. And so let's say I want to maintain 55. Now, you'll notice that when you do this, the heating coils disappear automatically. And we did that on purpose because there's quite a few VAV systems out there which are cooling only. So there's no heating source in the unit whatsoever. It can only provide cold air. And all the heating is provided at the zone level with reheat coils or zone valves or something like that. But we can still activate heat. I can just do config heating. And we'll see that this menu has changed a little bit. So now we can enable our morning warm-up sequence, and we can drive our heating outputs based on the return temperature. So the morning warm-up will only come into play if outside temperature is below 55, and if our return temperatures are below these values right here. And there is a timer on it. So the morning warm-up sequence will stop when either the timer has expired, so let's say we could put 60 minutes, or if the return temperature has reached the temperature which we want to. So let's say I want 69 and 66. So let's say in the case of the system, when it becomes occupied in the morning, the return temperature is at 65. So in that case, DO4 and DO5 will turn on. So it'll turn on both heating stages. Once return gets above 66, then we'll turn off heating stage 2, but the first one will remain on until we reach 69, or if the timer expires. So one or the other. And we're also able to force the zone dampers at a specific position or a specific flow if you want to. So you don't have to do this function. And the main reason I say that is because some zone the zones are always looking at the supply temperature and they're comparing it to their own space temperature. So if a zone is calling for cooling, let's say 65 in the space, and then it measures that coming from the unit, there's about 80 degree air or 90 degree air because the unit's in heating mode. Well, then the damper is going to want to open automatically without me having to give it the override command. So the VAV controllers are smart like that already. However, we had some customers who really needed that zone damper override, so we decided to include it nonetheless. And here at the bottom, we just have a low supply limit, which is just to make sure in case the unit, which is, let's say, trying to supply 55 degree air all day long, in case that temperature starts dropping, it gets below 50, it gets below 48, it gets below 46. Well, now we can start turning on our heating outputs as a safety precaution to avoid the supply temperature from dropping too low. And now when I come back here, so I see that the heating coils have appeared, and we can see here that says cooling set point 55. So we can tell what the set point is right now. Okay, now we have the bypass damper. So in this case, we would leave it as is if it were a VVT setting. But since I'm doing the supply temperature, well, let's simulate a VAV application. So it's actually quite simple. Just to config edit display, pressure control mode is going to be a variable frequency drive. I press on apply, I get home, and here we go. So the variable frequency drive has already, the graphic has been updated. I can see the actual voltage being applied to it, and I can see what the static pressure is. I don't have anything actually actually connected onto my controller because it's just a demo board. I can go into the settings, go config pressure, and then here we set up what's the set point we want to maintain with the differential, what's the input range. So the static pressure transmitter which we're using, we can use 0 to 1 inch, 0 to 1.5, 0 to 2, or 0 to 2.5. And what's the voltage range of the transmitter. So most commonly we use 0 to 5 volts, and the 1 to 5 volt, that's in case the signal is a 4 to 20 milliamp signal. So if we just add a little resistor, then it converts the 4 to 20 into a 1 to 5. But most often people use the 0 to 5. And then here we can play with the settings. So we typically want reverse acting for a variable frequency drive. As the pressure goes below set point, we want the VFD to ramp up. And once we go above set point, we want the VFD to slow down a bit. So that's reverse acting. And we can still put a minimum and a maximum voltage in case we determine that 3 volts as a minimum speed isn't fast enough. Maybe we'd like to set it at 3.6 volts, that we determine that that's a more adequate minimal speed. So I could just change this to 3.6 volts, and that's it. Okay. All right. So that's it for the VFD. If ever it was a bypass damper, well, if I just go back to the menu, the top half is exactly the same, and the bottom half, it just changes from drive settings to damper settings. And we just want to know whether it's clockwise or counterclockwise. Just to make a little note, we do not use a VC2000 for the bypass damper. We simply control it with a 0 to 10 or 2 to 10 volt signal. So any modulating actuator will do. Do not use a ProLon VC2000 for this. And then the last menu, which I wanted to show you, was the network other. So here's where we have those other features. So there's the morning warm-up for the zones, where I could choose to disable zone outputs based when the system becomes occupied in the morning. So I could say for the first 60 minutes, I'd like to disable all analog outputs on all the zones, but I only want that to apply to zone number 2. So in this case, only zone number 2's analog output will be disabled. Zone number 1 analog output will still be allowed to turn on. Here we have the cooling priority zones. So you can choose which zone is a cooling priority zone. So let's say zone number 1 is a conference room, or maybe it's like a corner office with a lot of windows, and in summertime it can get quite hot, quite sunny. So we might want to choose that zone as a cooling priority. In the middle here, we have our outside temperature overrides. So here's where we can choose to disable output based on outside temp. So I could say if outside gets below, so let's say 32, actually no, let's do this the other way around. If outside temperature gets above a very warm temperature, let's say if outside gets above 85 degrees Fahrenheit, well, I'd like to set my peripheral heating outputs at 0. So in that case, that specific zone, once again, we can set the participation. Who does it apply to? So that particular zone will not be able to turn on its outputs if outside gets above 85 degrees. In the case of that large showroom, such as the example which I used before, in case a large showroom with a lot of windows and there's a three-way hot water valve, well, maybe I could say if outside gets colder than 32, maybe that specific output, I want it to always be open at least 25%. So at least we're getting a little bit of heat into the space, even though it is satisfied, but I know that it's a large window area, and when it gets colder than 32, that the cold creeps right in. So at least with this, we'll be giving the zone a chance. And then right here at the very bottom, we do have the zone damper override right here. So this is not a sequence. This is a tool. It's like a general command for all zones to go to a specific position. So I could tell everybody go to 50% position, or everybody go to 100% or 0%. You can make them go based on flow. So this is more for the pressure independent controllers, whether we want them to go full flow, half flow, minimal flow. So we just put the percentage, or we can go simply based on minimum or based on maximum. So what's nice about this is that it doesn't matter whether the controller is pressure dependent or pressure independent. He's just going to go automatically to his maximum setting, whether it's one or whether it's the other. So, okay. I think that just about covers everything that I wanted to show everyone today. Sophie, do we have any questions?
We do have one question in the chat.
Okay. Okay, I see it. Can you explain the different ways the zone controllers can be addressed? Yes. So with the, actually, hold on. I'm just going to go get something. We'll do this here. Oh, wrong one. I'm just going to go dip into another PowerPoint, which I had. Okay. So for the M2000s and for the C1000s, the addressing is done through dip switches. So on the M2000, you'll see it's in the center, kind of at the top, and it's visible as soon as you look at the controller. On the C1000, they are not visible, so you do have to remove the cover. And we use the first 7 switches, even though there are 8, we only use the first 7. So each switch number, as we can see in red, has a binary value associated with it in green. So whichever switch you've pushed up, we add the binary values together. So in the case of my rooftop controller on my demo board, I have switches number 3 and number 5, which are up. So 3 is binary number 4. And switch number 5 has the binary number 16. So 4 plus 16 gives number 20. So that's how we do the addressing for the M2000s and for the C1000s. For the VC2000s, well, this one does not have any, so the VC2000 does not have any dip switches on it. So there's two ways. Either it's with a T1000 sensor or a T500 sensor, so any of the wall sensors with a digital display. And you'll see as soon as you connect the wall sensor into it, we'll see a screen, kind of like we see here on the T1000. It's going to say set the address. So you just move your finger on the touchpad and you can change the address. And the VAV controller will tell you right away that it doesn't have an address because we see the yellow status line is solid. So when the yellow status LED light is solid, it means that there's no address present. So that's a quick visual indication to know the VC2000 has an address or not. Once you do address it properly, that status light will disappear. Another way to address them is with the software. There's a service pin on the controller. So once you start the addressing sequence, so let's say I had another 3 controllers which I wanted to address, I could simply right click here and I hit assign addresses. So what's the first address I want to assign? Well, I know he's 1, he's 2, he's 20. So let's say I'll start with number 3, and I have, let's say I've got another 4 controllers which I want to address. So now he's waiting for you to go press on the service pin on the controller. So at the bottom of the controller, right below the terminals, there's a little sticker which says serve, and there's a little image of a wrench. So just get a little control screwdriver and you push down on the button, and then you'll see the status light will disappear and that controller will be address number 3. So that's how we do the addressing. I saw another question pop up on my side. If you have a VAV system but have pressure-dependent VC2000s, okay, how would you set up the VC2000 with reheat? Okay, so this is, let's say we take this example. So right now, this controller, this rooftop is already configured for a true VAV system. And let's say we wanted to follow the rules. I just want to make sure that it's a variable frequency drive instead. Okay, so here's our true VAV rooftop. And then with a pressure-dependent VAV, well, there's nothing stopping you from using this. So here's a pressure-dependent VAV. Let's say I have a reheat coil. So let's say in this example, it's a staged reheat. So I'm going to go onto the digital output, choose digital output, special function here at the bottom. We're going to choose duct heater. I'll press on apply. And then I go back. And now my duct heater is going to pop up. And I can see that the digital output is here. And I could just right click and rename it and call it the reheat coil. Okay. So this one is only going to turn on based off of a heating call. And so let's say I go onto my zone here, and I'm going to change the set point right now. So I'm going to force it open. Well, I'm going to force it into heating mode. So I just pushed the set point way up. And now, as we can see, it's in full heating mode. I can see my duct here turned on, but look what happens. My damper is now closing. Now we'll see at what position is he going to close at. So he was open 100% because he was calling for cooling, and he assumed that there was cold air coming from the unit. But now that there's hot air, that is asking for heat, now the damper is repositioning itself to the reheat position. So there are actually 2 minimum positions for the damper. There's the minimum position normally, and then there's the minimum position if the reheat coil has been activated. So often in engineering plans, when looking at at a VAV box schedule, you'll see the minimum CFM, maximum CFM, and then there's a minimum reheat CFM or position. So in this case, if I just go onto the damper, so here we go. So as we can see, here's my damper. Minimum is 10%. However, in a duct heater setup, so right below it, we have the minimum position is 30% when the duct heater reaches at least 25% output. So since it's a staged output, it will only ever be 0 or 100% the output. So we're okay with that. And in case it was a modulating three-way valve, so now it's not just open close, but it's a ramp, well, then we can say, well, once we've achieved 25% of the output, only then do we want it to go to the minimum reheat position, which would be 30%. Okay, so I hope I was able to answer that question. Okay, Sophie, do you have any other questions?
No, I don't have any more questions.
Very good. All right, well, that concludes today's webinar. We just wanted to show you how ProLon can control different types of zoning systems. Feel free to contact me or anybody else at ProLon. If you guys have any questions whatsoever, we'd be more than glad to help you out. So once again, my name is Daniel Cohen, and I would like to thank everybody for attending the session today.
Thank you, everyone, and have a great day.